Okay, in this lesson we're going to do a couple of applications of transformations, and the reason this is listed as applications to computer graphics is because we're going to start mapping two-dimensional coordinates onto a plane in 3 dimensions. And the general idea of this is if we want to kind of make things move the way they do in 2 dimensions, but we'd like to show some kind of depth. So think about the original kind of animation. They would place maybe a background on a screen, and then they would let things run in front of that screen, maybe act things out in different layers. So what we're going to introduce today is this idea of homogeneous coordinates, where we place the 2-dimensional coordinates on a 3-dimensional plane that we could choose here. We're choosing 1 to introduce all of these transformations because then our transformation doesn't have to be scaled by anything. We're putting it at kind of that distance of 1 away from kind of the screen. That way, whenever we want to do something like, let's say, we want to translate the point, as we're going to do here, maybe shift it up or down, left or right, that doesn't have to be scaled by anything when we're using our matrix. So our first translation, and again, if you're not into the computer graphics or the kind of animation application of this, you can also think about this as just another way to represent transformations using a matrix. And think about it kind of as 3-dimensional coordinates, but our coordinates go all in 1 plane together. Okay? All right. So our first translation, and there will be, transformation. There will be about 6 transformations we'll cover in this lesson. I know it says 5. Here's 6. Okay, 6 transformations, and this is number 1. So if you're looking for things to add to your note card, this would be the first thing. This matrix right here. When we were in 2 dimensions, we didn't have a matrix. We weren't given a matrix that was able to translate the points, shift them right or left, up or down. And that's because we couldn't figure out how to just add to a point without scaling it, or adding a value that wasn't in fact related to the y value as well. Here we can add independent values h and k to the x and y components, and they don't have to be related at all. We can't do that in 2 dimensions. So this is one of those transformations we could only do by translating it into homogeneous coordinates, adding that extra coordinate onto the end to put it in some kind of flat plane in 3 dimensions, and then we were able to use a 3x3 matrix to do that. And so this is a good example of when, if we choose a different plane to place our points in, let's say that I wanted to move x to the right by 2. So if I choose the plane 1 to represent my points in, I could just make this matrix 0, 1, 0, 2, and whatever we want to do. Maybe I want to shift y down 4. But that will only work correctly if I've made this homogeneous coordinate using z equals 1. If I had said, let's say z equals 2, and I want to add or move x2 to the right, I in fact would then have to put a 1 here. I would have to scale my transformation based on what plane I was in, and then I would have to put if I wanted to move down 4, and have to put a -2 here. And that's why, for simplicity, we're just going to leave this bottom component as 1. That makes writing the transformations a lot easier to understand. Okay, so homogeneous coordinates, projecting things onto the z equals 1 plane. Okay, and our first transformation is a translation, adding h to the x component and k to the y component. Now our second transformation is about rotating, which we already did in 2D, but I wanted to do a tiny proof, and it doesn't look like my picture printed here, so I'll go ahead and just redraw it real quick. And this actually helps because I'm going to then correct some of this here. So I am going to say the original point was x, a vector, the point xy, and that is theta degrees or radians from the x-axis. Okay, so we're rotating around the origin. If I want to then rotate this point, and maybe this isn't rotated quite correctly, here by another phi degrees or radians. Okay, so mapping it this way. Okay, our distance from the origin, r, does not change, but we have new coordinates, a new vector, that's w1 and w2. Okay, so to figure out the transformation to get from, and by the way, this is r here and r here, okay, are the same. To figure out what transformation matrix will take me from this point to this point, I need to think about the angles. And I used phi here, not because this is the same phi as in multivariable calculus, but because I needed another angle measure. So forgive me for using something that we're familiar with. But here we get the x equals r cosine theta, and because I didn't have my picture here, I was able to relabel my picture. If you're using the filled notes, this has been typed as x equals r cosine theta, but if you're using this angle as phi and this angle as theta, you'll need to switch them so the proof makes sense. And you can check out my filled notes for that too. Oh, actually maybe I didn't post them that way, but hopefully this makes sense. So x equals r cosine theta, y equals r sine theta. Our new coordinates will be r cosine of the two angles added together and r sine of the two angles added together. Using our pre-calculus knowledge, which I know you have not forgotten, I can split up those two formulas into r cosine phi minus r sine theta sine phi, and I messed up here. This should be cosine phi right here. Okay. And actually, you know what? I'm so sorry, guys. I'm going to go back and I'm going to label this one phi and this one theta so it matches your diagram, because I want to make sure we're all on the same page. So this is phi and this is theta, which then means I need to change these two formulas from their original state and write that x equals r cosine phi, this angle, and y equals r sine phi, this angle. Okay, that doesn't change the fact that I needed to alter this formula here, but that then makes my substitution clear. I can substitute this x and y in for the r cosine phi and r sine phi, and I will get that my new points are actually x cosine theta minus y sine theta, and x sine theta plus y cosine theta. So if I think about this as a matrix that is being multiplied by the vector x and y, okay, I can separate out the x and y into a vector on the right and use my cosine theta, sine theta, or negative sine theta, cosine theta as my matrix. Now, this works for 2 dimensions, and we actually did an example like this where I had you rotate 90 degrees, which is why it only included ones and zeros, and negative ones. But if we want to do this with homogeneous coordinates, this is going to be our counterclockwise rotation about the origin. I want you to put a star by that, because there are some examples in the textbook that want you to rotate about another point. In order to do that, you're going to need to translate your matrix using the above, this matrix up here. Translate your matrix so that the center you're given is the new origin. Then you can rotate, and then you can transfer back to the original place you started, which was the original origin. Just to clear up some confusion if you're actually doing the homework. LOL, I know that may be only like 3 of you. But this is our matrix number 2, okay, our transformation, rotation about the origin. And this phi here is the angle that you will be rotating around the origin. Okay, a couple more transformations here. Okay, we've already done reflections through y equals x. This has been the same as 2D. Okay, this is the same matrix right here, and actually you can use that format. Any of the matrices that we used from chapter 1, you could translate them into homogeneous transformations just by putting them in the upper left hand corner and adding a column of zeros, a row of zeros, and a 1 in the bottom right corner. And then there's one more that I just wanted to mention. So this is transformation number 3. Transformation number 4, the reminder to scale the points. Okay, I can do that by putting what I want to scale them by along the, and this is an S, what I want to scale them by along the diagonal. Again, leaving Z, we want to be in the same plane, so I'm leaving Z alone, but I am changing X and Y independently, scaling them by different numbers. And then the 5th transformation is not really a transformation, but it's just kind of a concept, and that's if you want to do multiple transformations at once. You need to line them up in the opposite order that we think. And that's because since matrix multiplication is not commutative, it's associative, I need the first transformation to be right next to the point I want to transform. Okay, because these two will be multiplied together first. And then whatever comes out of here will be multiplied by the second matrix. And then after that we get that result, then we'll multiply it by a final transformation. But the really nice thing about this is it has to be in this order. What you want to do first, then second, then third, from right to left. But if we don't want to have to go through 3 different matrix multiplications, what I can do is I can actually, before multiplying my point to the first transformation, I can multiply all 3 of these transformations together so that I get one big matrix. And if I specifically have lined them up in this order, then that one matrix created by multiplying these 3 things together will do the transformations that I want in this order. So let's take a look at what that might look like in an example. So I am going to find a 3 by 3 matrix for both of these points. It's going to be a composite 2D transformation. We're going to use our homogeneous coordinates. So again, I am going to use x, y, 1. And I'm not trying to actually translate a coordinate here. I'm just trying to find a matrix that will describe these transformations in this order. So if I want to first translate by -2, 3, that means the first matrix that I would multiply by would be 1, 0, -2, 0, 1, 3, 0, 0, 1. That would be the first thing I would multiply my point by. The second thing I would multiply my point by would be a matrix that scales the x coordinate by 0.8 and then the y coordinate by 1.2. Okay, and I could, if I was going to scale a point where I was going to plug a point in, I could plug it in right here and multiply it to this matrix first, and then whatever I get out of here, I would multiply that to this matrix second. But I am just looking for a matrix, one big matrix that will do both of these transformations at once. And as long as I place them in this order, first transformation, then second transformation, and I multiply them together like this, I should get that one big matrix. So I'm going to go ahead and multiply that in my calculator. So I've got alpha zoom, I've got a 3 by 3 matrix, and I should type them in exactly the way I wrote them down. Please show your work. Okay, scrolling, oops, missed, 1.2, 1, and then another alpha zoom, 3 by 3 matrix, 1, 0, -2, 0, 1, 3, and then just a 1 on the bottom. And there you go. And you could have done that in your head too. But just to remind you how to multiply matrices in your calculator, my matrix that will do these transformation, first translating by -2, 3, and then scaling the x coordinate by 0.8 and y coordinate by 1.2, will be the matrix 0.8, 0, -1.6, 0, 1.2, 3.6, and 0, 0, 1. Again, leaving that z component alone. Okay. All right, so I will let you do this one on your own. But remember that first we're rotating points by 30 degrees, so we're going to use our rotation matrix. And then we didn't talk about reflecting through the x-axis, but a reminder, if you reflect something through the x-axis, you are making the y values negative. So we'll let you try that one if you want to pause here and check the filled notes. Try to make a matrix, like I did here, that first rotates the point 30 degrees and then reflects through the x-axis, aka making the y values negative. Okay, don't forget your unit circle. But there is one other type of transformation that we want to talk about, and that is a perspective projection. So our idea, oh, and I'm sad that I didn't get to, here, let me show you my filled notes instead. Okay, I don't know why the pictures didn't print, but we are again going to use homogeneous coordinates, but instead of, we're going to project a 3-dimensional point onto a 2-dimensional surface. But it's going to be in reference from a certain perspective, which we're going to line up with the z-axis. So our coordinates are already in 3 dimensions, which means that our homogeneous coordinates, the coordinates that are similar to this in 4 dimensions, are x, y, z, 1. And in general, we could even use x, y, z, h, as long as we know that the original coordinates will be x over h, y over h, and z over h. Okay, so our idea is to be able to take this 3D object and project it onto a 2D plane, but we want it to be scaled appropriately so that the viewer could feel like they could see the depth in the image, and that's the most important part. This scaling by H at the end is what's going to help us define the kind of the depth of our image. And you can see that the coordinates we get here come from these proportional triangles. This is, in fact, AP geometry. So our new x coordinates here, we can make similar triangles by measuring x star, which is this length over here, and the length of the big triangle D, okay, and comparing that to little x, the original x value, and D minus Z, the difference between the perspective and where the point actually should be. Okay, so we're getting some similar triangles. All of this leads to our new coordinates as x over 1 minus z over d, y over 1 minus z over d, comma 0, comma 1. When we do the transformation with this matrix, this is not what will come out when we initially multiply by the points. We will actually come out with x, y, 0, and then some h value here. So we will need to scale our coordinates by whatever this value is in order to get our new coordinates. And that will be one of our steps. The transformation matrix for this is actually super simple, and I'm going to move over here again. This is transformation number 6 that you need to pay attention to in these notes. Notice that I'm leaving x and y the same throughout, but then in the end, I will go ahead, because this is what will come out of my matrix, I will need to then scale everything, divide everything by that h value in order to get the correct new coordinates, the coordinates that I would want to plot on my two-dimensional xy plane, z equals 0. Okay, so we're going to do one example together, and I'll take it step by step. So we're going to project a triangle, and it's got 3 different vertices here, obviously, because it's a triangle. And we want to find the image of this under a perspective projection. When we talk about the center of projection at this point, which will usually be labeled on the z-axis, we are going to say that that is our kind of depth from the screen. That's our perspective. Okay. So step 1, because we don't want to do this process like 5 billion times, we're going to put the homogeneous coordinates. I can't spell homogeneous. Okay, there we go. Into a matrix. So that means I'm going to put them in each as their own vector vertically. So 9, 3, negative 5, 1. Again, homogeneous coordinates, letting the 4th dimension be 1. 12, 8, 2, 1. 1.8, 2.7, 1, 1. Okay, so those are my homogeneous coordinates. That we're going to multiply this entire matrix by the transformation matrix, so we transform all the points at the same time. Step 2, transformation matrix. Transformation. Sorry guys, it's getting late. Okay, and using the format from the other side, we're leaving x the same, y, leave y the same, make z 0, and then our 4th dimensional point will be where we have negative 1 over d, so negative 1 over 10. Okay, it's kind of like the opposite reciprocal here. And then z, or this last one, is 1. That's our transformation matrix. Okay, step 3, multiply. And remember that my transformation matrix will come first, and then my coordinate matrix will come second. So I will be multiplying 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, negative 1, 10th, by the matrix 9, 3, negative 5, 1, 12, 8, 2, 1, 1.8, 2.7, 1, 1. And when I multiply those two things together, I'm not going to show you in the calculator because I think we've done enough of that for today. We will get the matrix 9, 12, 1.8. All the x coordinates did not change. 3, 8, 2.7. Again, did not change locations. Our z coordinate now got mapped to 0, okay, because we want them to be in a two-dimensional plane, so we mapped it to x equals 0. And then our scale factor here, that's kind of what we're putting in the bottom, are 1.5, 0.8, and 0.9. Okay. Now, to find my actual coordinates, to find my actual answer for the image of, the image of S under the perspective projection is going to be these coordinates divided by the scale factor. So my new coordinates are going to be 9 over 1.5, 3 over 1.5, 0, 12 over 0.8, 8 over 0.8, 0, and 1.8 over 0.9, 2.7 over 0.9, and 0. These are my new coordinates, and you can reduce them if you would like to 6, 2, 0, 15, 10, 0, and 2, 3, 0. Okay, so those are my new coordinates. That will make up my image of S under this perspective projection. So don't forget the last step, and I forgot to write it down here, step 4, scale the coordinates. Okay, and that's because when we map something, if something is further away from us, it seems smaller. So if one of the corners of this triangle had been further away from us, let's say like this one, but this one had been closer to us, one could appear larger than the other. So we want to make sure that we kind of retain that feeling of distance by kind of scaling and shifting the coordinates so that it's still, on our 2D image, on our flat image, it appears as though we have some depth in our triangle as we did before. All right, so that's it. Those are our 6 transformations.